Welcome back, ladies and gentlemen. So, like I said, this is the second video of going through some of these extraordinary, or not extraordinary, but these extra problems that we were talking about in problem solving in particular for this week, and focusing around some of the basic geometric optics, okay? And so I'm going to be going through 4 problems here in this video. Some of them of relatively simple complexity and others of a little bit more intensity. That way we can make sure that we're all on the same page. That way we make sure that we can move on for the next homework and for the next couple of classes before we move on to bigger and better things, that we have all these basics and foundations, mostly about the idea of what it means to be a wave, the basic properties of waves, the law of reflection and the law of refraction under our belt, and then we move on from there, okay? So hopefully this will be illuminating. Boom, best I got. Okay, let's jump right to it. Okay, so these are the first 2 problems that I want to go through. Jumping right into the first one, okay, what do we see here? We see that we have a waveform given, okay? Biggest thing to notice here, right, is that the waveform is given. The wave does not start from 0. It starts its climb already at 14 and descends down to another negative 14, which means that we basically have its amplitude right out the gate because we start from the amplitude. That's also important because that's going to help us identify what kind of trig function this wave is, because we know that sines start at 0, cosines start at the maximum or minimum, okay? The other big thing to notice here is that on the x-axis, we're not given time like we were, or like the problem I did in the previous video. In this one, instead, we're given the x-axis in meters, which means that when we're peeling some information off of this wave, that the piece that we're going to be peeling off, instead of being the period like it was last time, the time required to complete one cycle, here we'll be peeling off the length of one cycle itself, namely, we'll be peeling off the wavelength. So let's make sure that we can do all this and drop it in real quick. So having said that, let's peel off all the simple things that we can. We see right away that the amplitude A is 14. We just said that we're going to peel off the wavelength from the x-axis. Let's highlight where this wave begins. Goes, and then we've done one full cycle. That's one full waveform. We drop that down and we see that this is at 4 meters. If that is the wavelength, then right away we know that k is 2 pi over the wavelength, which is also known as pi over 2. If we know that the wave has a speed of 100 meters per second, then we know that the velocity, as always, is wavelength times frequency. So the frequency then is the velocity divided by the wavelength, and the velocity being 100 meters per second, the wavelength being 4 meters, this is 25 hertz. If that's the frequency, then we know that omega is 2 pi times the frequency, which is also known as 50 pi. We also then know that the period is 1 over the frequency, which is 1 over 25. Last but not least, if we know all these quantities, we can put this into its standard mathematical formula. A as a function of x and t then is the amplitude 14 times the trig function, which we've already discussed. Here is cosine. K, which is pi over 2. The variable x minus omega 50 pi times the variable t, and we have it. Yes, a0 cosine kx minus omega t is the standard form, and there we have it out. Okay, so again, same type of problem that we did a couple of days ago in the last video, except in that one I gave you the time axis, I'm sorry, the x-axis as time. Here I gave it to you as length. Really, all that it boils down to is that we just got to be careful as to what is given. That way we make sure that when we're peeling information off, we're peeling off the proper information. Okay, here's a different one. Let's get a grasp of this sketch before we start solving it, okay? We have one of these like recessed light bulbs, okay, sitting in the ceiling. So it's not drawn to scale exactly, right? That bulb is supposed to be exactly up against the ceiling, okay? And it's 1 meter from the wall, okay? And then on that wall, okay, starting from the floor and going up, we have a 2 meter tall standing mirror, okay? And so on the other side of the light, you know, that's why I said it's one of those recessed ones. Maybe it's like one of those, you know, halogens that bulbs out like this, right? We have some sort of light blocker so that the light can only go towards the wall. Imagine it's like one of these display lights, okay? So it's not beaming down onto the floor below it, okay? If that's the case, right, that means that some of the light rays, in particular the one in green, right, is going to bounce, is going to leave the light light bulb and bounce off of the mirror and project onto the floor. If that's the case then, okay, that's the line in pink there, I'm asking how long, what is the maximum length of the light smear on the floor? Again, if you have a 2 meter tall mirror, there's 0.5 meters between the top of the mirror and the ceiling, and the light bulb is 1 meter away from the wall. Okay, sounds like this might be complicated. Sounds like this might be tricky. Turns out it's really not, okay? Let's first rationalize why I only drew one light beam. There's infinite amounts of light beams that draw, or rays that leave the light bulb, okay? But anything north of the mirror, anything above the mirror isn't gonna bounce off of the wall and come back and contribute to this light smear, right? It's a mirror. A mirror is really good at reflecting, which means we're probably gonna be putting to use the law of reflection here, okay? Any other beam, okay, and I'll just do this quickly in like purple, let's say, any other beam that, let's say, came in at a lower point in the light beam is going to cause a lower point. It's not going to give us the maximum reflection. Namely, the only one that we really concern ourselves with is really the beam that hits the uppermost point of the mirror that will shine it back down. Then we know that that beam, which I've drawn in green, which hits the very top point of the mirror, is going to bounce or reflect off of that mirror and come down and project itself onto the floor, which allows us to use the law of reflection. So it's my argument to you that with all this information, that's enough information there to just do some geometric or ray optics, okay, to figure out how these angles relate to one another and how we can use that to find the unknown distance x. Let's jump in, shall we? Okay, in the upper triangle, right, when you leave the light beam, okay, you leave the light beam and you're going towards the mirror, right, we drew the vertical in over here. We said this was theta incident. Let's take a look at that triangle. That triangle, we know we said is 1 meter away from the wall, and the height on the other side, which is absent the mirror, is 0.5 meters. Which means that by similar triangles, or by these, whatever you want to call these alternating lines, right, theta incident can also be found up there. So that tells me that theta incident is going to be the inverse tangent, and this is just no physics here, this is just geometry, of the opposite, 0.5, divided by the adjacent, 1, which is going to be about 26.6 degrees. So that angle, which first starts here, then becomes theta incident. But then we know that theta incident is the same as theta reflected. So theta reflected then is also 26.6 degrees. There's our physics, yes? That's the law of reflection happening in real time. What happens, that ray continues down, okay? And it gets down here, and then we had this line over here, which was the unknown distance x. And then we had this line here, which is 2 meters. But now, again, if this angle is theta reflection, that means that theta reflection, again, by the perpendicular angles comes right down in here, which means that now we know that that angle is a good old 26.6 degrees. We know that 2 is opposite of it, and x is adjacent of it. So once again, we can use the definition of tangent, right? That the tangent of 26.6 degrees is equal to the opposite 2 over x, and that we can now solve for x. And what we see then is that x is 2 divided by the tangent of 26.6 degrees. We take this number and we put it into our calculator. And what we see is that this length is just about 4 meters. So for this type of geometric scenario, the longest we can get this light at a distance of 1 meter 0.5 meters from the ceiling, hitting a 2-meter high mirror is 4 meters across the ground. Pretty awesome that we could even figure something like that out, right? But all we had to do here was be patient with some simple geometry, and the law of reflection, which as far as a physics law goes, couldn't be any easier. Theta incident is equal to theta reflected as long as we draw it with respect to a vertical. Let me make a quick comment on that. I know it's weird to draw a vertical coming into a horizontal here, but think about this, right? We're talking about how the light comes incident to the surface. The surface happened to be on the wall here, and so therefore vertical, or perpendicular if you will, had to come out this way, which is why we drew the green dashed line as such. Okay, so let's keep that in mind as we practice more and more of these problems. Let's try another one with the law of reflection just to make sure that we're all on the same page before we jump into the law of refraction. Okay, so let's get a grasp of this one too. I kind of like this. This is an interesting problem that shows you really the power of geometric or ray optics, again, without doing not too much work and just some simple geometry, right? Let's say you have a person like me, height h, you know it, right? So let's say it's a number that you know, okay? And you ask yourself, you know, if I have some mirror on the wall across the way, right? Maybe you're standing in a bathroom, right? You're looking at the bathroom mirror. What is the minimum size L of that mirror that would have to be to fit my entire body into it? Right? And I don't mean like width-wise, I mean like my entire height, like from head to toe. Believe it or not, you can figure this out with not too much trouble just by using the law of reflection, because it's a mirror here, and again, just by using some simple geometry. So I gave you a sketch down here, so let's make sure that we understand the sketch, okay? So the person's height h, there's our person, okay? What does he do? His eyes are what take in the information, okay? And the mirror is across the way there, that size L, okay? And so again, right, what are the important light rays that your eyes take in? The important ones are the ones that come from the top of your head, bounce off the mirror and hit your eyes, and the ones from your toes that hit the mirror and come back and hit your eyes. Because if you can see the beam reflecting from the top of your head, as well as the one reflecting from your toes, you have to see everything in between, right? So those, kind of like the last problem, right? How it was only the one that was at the top of the mirror that mattered here, right? Here we're saying it's really the beam at the top of the mirror and the bottom of the mirror if we want to ask ourselves about what's contained completely in the mirror. Cool. But if that's the case, we then have to ask ourselves a couple of, or we have to then say, okay, well, we need the piece that bounces off the top of our heads. We need the piece that bounces off the bottom, our feet, okay? And if that can happen, then we would be able to therefore fit our entire body. And so we want to know then, how does that length L relate to the height of us? I'm going to zoom in a minute and kind of draw this a little bit better, but notice I drew some separators here, right? That I called H sub E in green there is the height from the top of my head to my eyes. And then I drew T sub E in there, right, in red, which is the height from my toes to my eyes, okay? And so if you knew from my head to eyes plus toes to eyes, that's another way of saying my total height H, which is why I built this equation right here, because we're going to need to know how all of that relates in a little bit, okay? So let's jump over to the mirror. Let's zoom in on the mirror and see what's happening at the actual reflection. Just like I did before, I'm going to draw the mirror in blue, right? So let's say that this is our mirror and we're zoomed in here, okay? And I'm not going to be able to draw this completely to scale, but how does this go over here, right? The light beam comes in from the head and bounces off to the eyes. And this is a pretty narrow triangle, right, as we've seen from over here, right? Okay. And what does it ultimately do? Right, it gets to our eyes over here. Okay. What happens when that light beam comes in? What do we absolutely know about it? We know that if we called this theta incident, then this would have to be the same as theta reflected, right? Those two angles would have to be the same by the laws of reflection. Okay, cool. What happens from the toes? This one's going to be a bit steeper, right? But again, same thing has to happen, and that means that the theta incident in red has to be the same as the theta reflected in red. Cool. Okay, now why did I want to draw this over here? I want to draw this over here because remember, this length over here, the mirror, is L. How does that relate to the lengths that we drew over here in green and in red, right? Okay, so if, again, I told you I'm not going to be able to really do this to scale, right? If we try to put back in my person, right? This was the top of his head. There's his eyes. Oh God, I told you it was not to scale, right? There's his feet. Namely, what am I really saying here, right? Is that we can now build a relationship geometrically between the line in blue, the length in blue, and where we actually had drawn in this overall TE and HE, right? Okay, namely, if we put back in this line right here, and so I'm just going to take the guy out because he is not instructive in this at all, okay? But what do we know? That if those are the eyes, we know that this line right here was what I called HE, namely the height from the top of the head to the eyes, which means that each of these little pieces here, these smaller triangles, if you will, is HE by 2. By the same token, this line in red, again, not drawn to scale, overall is TE, which means that this is TE by 2, TE by 2. And so if we take line segment by line segment and say, how can we find L, right? Do we then see that that segment in blue, I'll just highlight it right here, is this piece plus this piece, yes? Namely, L is equal to HE by 2 plus TE by 2. Well, wouldn't that be nice if we just had HE plus TE, because then we'd be able to relate this to the height H. Okay, well, let's do that. Let's multiply everything by 2. And we see that 2L is equal to HE plus TE. And we had a name for HE plus TE. That was how we started this entire endeavor back in black. And so we see that the height is twice L. So the mirror has to be at least half of your height to get all of your person in the mirror there. Pretty wild that we can even figure that out, right? Okay, not complicated physics-wise, right? We're just using the law of reflection, and then we're just drawing a bunch of lines, rays, and doing some simple geometry on it, which is where, again, we got this name of geometric or ray optics, okay? It really boils down to, in each one of these, figuring out which line segment is the one that would be of importance. That's good enough for the law of reflection. Let's jump to the law of refraction. Okay, so let's say we have this type of incident happening. We have a light ray that starts in n equals 1 or air, okay, and it hits this surface in black, which is made of glass. And so this whole area in here, which I will now erase, is glass. Okay, that whole area is glass. It goes through some glass of some thickness and then comes back out to an n equals 1 again. It comes back out to air. Okay, it comes in with an incident angle of 30 degrees. And so from that, let's say that some of the light gets through the glass and some of it reflects back off of the glass. So find what those reflection angles, incident angles, et cetera, are all the way down until you get back out the other side. Sound fair? This is clearly going to be where we're going to use the law of refraction because we're permeating through a surface and not just simply bouncing off, okay? So this is where we're going to have to make use of the fact that N1 sine theta 1 is equal to N2 sine theta 2. And I remind you that that's true across any interface, across any surface, okay? So yeah, that's true at the first surface, but it's also got to be true at the second surface, okay? So let's see if we can just use that and get through this 1, 2, 3. Okay, but let's just knock out the easy part first, because I did ask you that if some of the light is bounced back, how much, what direction does it bounce back? Ladies and gentlemen, okay, here we go. If this angle comes in at 30, what do we know about the law of reflection? Whatever it comes in with respect to a vertical, it's got to be the same as it comes back. This angle right here has got to be 30 for whatever it bounces back. So that I call theta S. That one is already considered done. But now what is I'm more interested in here is what is this angle theta R about the light that gets through. Okay, so here we have N1. So at surface 1, or the top surface, okay, what do we have? We have N1 is 1, namely air. We have theta 1 is 30. And then what do we have? N2 is that of glass, which is just something that we look up in our textbook. This is 1.52 glass. And theta 2 is the thing that we want to know. So at that top surface, can we use that law to figure out theta 2? The answer is yes, because we take a look at that, and n sine theta 1 is equal to n2 sine theta 2. We know, we don't. So solve this then for theta 2. And so upon solving for theta 2, we're really first solving for sine of theta 2 is going to be n1 by n2 times the sine of theta 1. Okay, let's get out our calculator. We take 1 and we divide it by 1.52. And we multiply that by the sine of 30 degrees. And that's going to be 0.32, 0.33. And then we take the inverse sine to resurrect the angle, and that gives us about 19.3 degrees. Oh, let's actually put that on a separate line. I apologize. Theta 1 is about 19.3 degrees. Theta 2. Okay, so again, remember, these are all measured with respect to a vertical, so that means this is the angle that we were looking for. Okay, and so now we can ask ourselves the question, if we get back and we go out the other side through some other index of refraction, through some other surface, it doesn't have to be air. Here I just drew it as air, but you could have bumped back out and went through any other index of refraction. What do you pop back out as? Okay, so again, we need to then just be really careful here and say, well, that was theta refracted. If you take a look, that's this angle here. By our laws of geometry, that's got to be the same as this angle here, which is an angle that is drawn from a vertical. Okay, so that is theta R is going to be the same as our incident angle. So we can then use N1 or N2 now, if you will, sine theta 2 is N3 sine theta 3, namely across the second surface. Okay, where now we know N2, we know theta 2, we know N3, and we want to solve this for theta 3. Here, N3 is back to 1 because we're back out in air again. So then the sine of theta 3 is going to be 1.52 divided by 1 times the sine of 19.3 degrees. And I think it's going to be pretty clear where we're going with this, but if you don't believe it, just crunch it away in your calculator there. Sine 19.3 times 1.52 gives us a 0.5, and then we take the inverse sine of that, the inverse sine of 0.5, and yeah, what do you know? We're back to theta 3 being 30 degrees. Namely, the way that the light refracts back out the bottom surface is back to the way it originally came in. Because we know the speed of light has to be the same as long as you're in the same medium. You started in air, you went through glass, which is why it refracted, but then when you got back out, it went back through air again, went back to its same speed. The index of refraction is the same, the angle's got to be recovered. how could you possibly make things like this harder? You can just make more surfaces. You can ask about lengths of these things, right? And just do more geometry like we just did with the law of reflection. But that's as much as there is to it, ladies and gentlemen. It really is not so bad. Okay, so I know we went through 4 problems in this one session, so the video is going to be a little bit lengthy, but none of these problems were of a tremendous high degree of difficulty. So please, go through these slowly, make sure that they make sense. These are going to become, we're just going to practice lots and lots of these during our problem solving sessions this week and for the videos this week. And this is also what the homework is going to be about. So let's make sure that we're all with it and all on the same page. As always, ladies and gentlemen, if you have questions, comments, complaints, or concerns, please do not hesitate to ask. I enjoyed making this video for you. I love talking about optics. I hope that I have helped you see the light on this, and I hope that you have a fantastic weekend.